In this video, we'll be learning about imperfections in solids, defects, and the types of defects. So let's begin. Here you can see that a solidification of a crystal structure is being displayed to you. So in the figure A, you can see that the small nuclei are being formed while a material is being solidified from a liquid state. So you can see that these small particulates that are called nuclei, which are formed in the figure A, and then in the figure B, while the more liquid is transferred into the solid state. So you can see that this nuclei are now growing ahead, and the gray area is still the liquid part. In the C part, you can see that again the growing is being further carried out while reducing the temperature, and in the D part you can see that now it is completely solidified, and there are some grains that are being formed due to the solidification. So this is a solidification pattern. We'll be discussing more about grains in the next slides. So in this we have types of imperfections. So we have point defects, we have line defects, we have area and interfacial defects, and we have volume defects. So in point defects we have vacancy atoms, we have interstitial atoms, we have substitution atoms. In line defects we have dislocations, which we'll be studying. In area and or interfacial defects we have grain boundaries, and in the bulk or the volumetric defects we have void, crack, inclusion, or a precipitate. So we'll be discussing these one by one. First, in a point defects in metals. So how does a point defect is created? So basically point defects are basically vacancies. You can see that here that there is a lattice of atoms, okay, and there is a empty site over here. So this site is called a vacancy. So the vacancy are the vacant atomic sites in the structure, as you can see over here, and this causes a strain or a distortion in the lattice. So what are self-intercessions? A self-interstitial are extra atoms positioned between atomic sites. So these also causes a lattice strain that sometimes the lattice has been stretched. As you can see that all these atoms, the atomic plane line is being disturbed now, and the atom is being stretched. Okay, so there is some strain put. So in self-interstitial, the atom of the same unit cell or the same lattice is being attached inside the lattice geometry. But in the vacancy you can see that this one of the atoms or several atoms are empty, so it causes an empty space. So this would cause a compressive strain. Next we have equilibrium concentrations of point defects. So if you want to find the number of vacancies or the total number of atomic sites, you use this formula. And this NV is the number of vacancies, N is the number of total atomic sites, and that is equal to the exponential of minus QV, which is the accretion energy, K, which is the Boltzmann's constant, and T is the temperature. Okay, so we can find the equilibrium concentration of the point defect. We also know that each lattice site is a potential vacancy site. That means that this, in the absence of this atom, we can create a vacancy over here. We can also create a vacancy over here if this atom is not present. So it can be any side. Okay. So now impurities in solids. You can see that the materials which are commercially being produced are never a pure material. So what is a pure material or a pure metal? A pure metal is the one which is consisting of only one type of atom. That is not possible. So, and the impurity or foreign atoms will always be present, and some will exist as a crystalline point defects. So we know that impurities are very important in our in terms of the physical properties or the chemical properties. That is why that is the reason why we usually form alloys rather than chemical compounds. So basically, alloys are impurity atoms added intentionally to induce certain characteristics so that the material performs well. For example, if we have a mild steel, so if we add chromium or if we add nickel in the mild steel, it becomes stainless steel that is used uh, in our kitchens, daily life kitchens, and other products as well. So to make it stainless, we have to add chromium or we have to add nickel, which is an impurity. But in this case, which this is beneficial for us because it increases the corrosion resistance of that material. Okay. So now let's discuss solid solutions. The addition of impurity atoms to a metal will result in a formation of a solid solution. So in the solution, we always know that there is a solvent and there is a solute. A solute is present in the lesser quantity, and the solvent is always which absorbs or which dissolves the solute inside it. So if there is a little difference between like and unlike bonds, then a solid solution can occur over a wide range of elemental compositions. Okay. So we have two types of solid solutions. One is the substitutional solid solution, and the other is the interstitial solid solution. So in the substitutional solid solution, you can see that atoms, the impurity atoms which are in the blue, which are represented by the blue spheres. So you can see that the impurity atoms are of a similar size to that of the host or the uh, parent metal. So you can see that the host atoms are replaced by certain atoms which are of the same size and or the same properties that form a substitutional solid solution. And this the atom is the host atom is being replaced by a foreign atom, or you can say that host atom is replaced by an impurity atom. Okay, so this is usually observed in alloying. Then we have interstitial solid solution. So in interstitial solid solution, you can see that these solute parts are very small. The impurity atoms are very small, and they are adjusted inside the interstices. You know, the empty spaces which are over here. You can see over here. So usually these atoms the difference between the radius of this the foreign atom or the impurity atom and the host atom is usually greater than 15%. So the size is very different. The interstitial atoms are very small so that they can fit inside the empty spaces, and these make up a interstitial solid solution. Okay, so now in order to judge that our solid solution is substitutional or interstitial solution, we'll be using a Hume-Rothery rule for that. In that the first uh, point says that the radius should be less than 15%. So for a substitutional solid solution, the radius, the atomic radius between of the host atom and the impurity atom should be less than 15%, and if it is greater than 15%, it would be making a interstitial solid solution. Then we have proximity in the periodic table. So the impurity atom and the host atom must have similar electronegativities. Then we have that same crystal structure for a pure metal. So are if you have an FCC structure of the host atom, so the most favorable impurity to make a solid solution, to make a substitution solid solution, would be that the impurity should also have that FCC structure. So the crystal structure should be similar, and also the valencies should be similar in order to make the uh, substitution solid solution. So let's do an example over here, that we have a copper nickel alloy system. So we have to check all these four conditions in order to comment that the solution is substitutional or it is interstitial. So we'll be checking the difference between the radius. First of all, we know that the radius of copper is 0.128 nanometers. The radius of nickel is 0.125 nanometers. So uh, uh, we'll be calculating the difference of radius, that is radius of copper minus radius of nickel divided by the radius of copper, because we are checking against copper, and then we'll be multiplying it by 100. So you can see we'll be getting this answer, that is 2.3%, which is less than 15%. So yeah, this is the first condition which is satisfied for the Hume-Rossby rule to make the substitution solid solution. Then rule number 2, we know that the nickel and copper both have FCC crystal structure. So it also says here that it should have the same crystal structure. So point number 2 is also satisfied. Then talking about electronegativity, so it says that the proximity interval, that is similar electronegativity. So we know that the electronegativity of copper is 1.9 and the electronegativity of nickel is 1.8. So basically these are not exactly the same, but they're almost same. Then the last tool is the valency. So both copper and nickel uh, have a +2 valency. You should remember that we're not making a compound over here. If we are making a compound over here, the valency should be plus and minus in order to stabilize the compound. But we are making an alloy, we are making a solid solution over here. So for this, both the valencies are in the positive. Okay, so all these conditions are have been satisfied, are favorable. So the solution would be, in the system of copper and nickel alloys, would be of a solid solution, a substitution solid solution. Okay, so now we have point defects. Continuing point defects, we have substitution impurity, impurity atom in the lattice. You can see that this is the substitution impurity atoms and the interstitial impurity atoms, uh, not on the regular lattice side. So you can see that they are substitution impurities and the interstitial impurities both. So in the real life, in the real life systems, we also have certain impurities which are not desirable. So in order to make our system very accurate, the solution very accurate, and that is, or as for a substitution solid solution or an interstitial solid solution, we have to uh, we should be making the system very efficiently, the the casting system or the alloy design very efficiently, in order to avoid these extra impurity atoms. Then we have linear defects, or we can say that dislocations. We discussed point defects Now we are discussing linear defects, that is usually caused by a dislocation. So a dislocation is a linear or a one-dimensional defect around which some of the atoms are misaligned. So we'll be looking with this on this figure. So misalignment of atoms due to the application of stress force that causes slip between crystal planes produces permanent plastic deformation. Berger vector B is used to measure the lattice distortion. So here you can see that there are two types of dislocations. One is the edge dislocation and the other is the screw dislocations. So in an edge dislocation, usually a tensile force is applied. Okay. um, uh, and you can see that there is a crystal lattice and these atoms are shifted over here. This is the basically the quantity of dislocation which is being measured by the Berger vector B. Okay, and this is usually caused by plastic deformation while we are applying uh, an external force. Here you can see that in an edge dislocation, the defects where an extra half plane of atoms introduced midway through the crystal distorting the nearby planes of atoms. So this is another view of the edge dislocation. You can see that while we are applying stress, so there is an extra half plane which is this one, okay, which is introduced while the application of force. So this the measurement of this is given by this Berger vector. You can see over here that this caterpillar analogy uh, clearly represents that this half plane is moving, and basically this is the dislocation which is moving throughout the lattice, and finally this the lattice is being distorted again. So for edge dislocation, the Berger vector and dislocation line are perpendicular. You can see that this is the Berger vector and this one is the dislocation line. So these both are perpendicular, while the Berger vector this and the dislocation movement, the dislocation is moving towards from the left to the right. So both of them are parallel, the Berger vector and the dislocation movement. And next we have a screw dislocation. In a screw dislocation, usually a shear force is being applied. Okay, so you can see that the the lattice is being teared out. You can see over here that, and in a screw dislocation, may be thought of as being formed by a shear stress that is applied to produce the distortion. As I discussed, that a shear force is being applied, and here is the Berger vector. You can see again this is the dislocation movement basically, because it is uh, you can see that you can see that a shear force is being applied, so it would be tearing out, the plane would be tearing out from here. So this figure can display a more effective diagram of screw dislocation, that you can see that a helical path or ramp that is traced around the dislocation line. This is the dislocation line. You can see over here as the forces being applied are the shear forces. So this is the Berger vector over here, and the dislocation line. You can see that Berger vector and dislocation line are parallel over here. Right, this is the dislocation line, and again this is the Berger vector, which is parallel, and the dislocation movement. The dislocation movement is in this direction. So the Berger vector and the dislocation movement are uh, perpendicular over here. So unlike the edge dislocation, the Berger vector and the dislocation lines are parallel over here, and the Berger vector and the dislocation movement are perpendicular. So here's this slide. Then we have a mixed dislocation. So in a practical application, in practical applications, we often get mixed dislocations because the when we are applying tensile force, so there are certain stresses that are generated inside the lattice, which are tensile stress and shear stress as well. So you can see that the mixed dislocation is being observed since the shear stresses are being generated, and that causes the screw dislocation, even though which if we provide a tensile force or a tensile load. Okay, you can see that this one is the edge dislocation. The plane is the half plane is moving up, and here we can see that the screw dislocation has been observed. Then we have certain surface and or planar defects, in which first of all we have an external surface. You can see that this external surface has been abraded. So obvious boundaries along which the crystal structure terminates, the surface atoms are not bonded to maximum number of nearest neighbors, which lead to higher energy state than bulk atoms. Surface atoms tend to minimize its surface area to reduce the surface energy. Then we have this is the main defect that is called the grain boundary. So you can see that while so this is a micrograph of a titanium alloy. So you can see that when this is solidified from the molten state, so these grains are formed. So this is one grain, this is one grain, this is one grain. These are now fine grains, so smaller grain as well. So all these are grains, and these lines, let me change the color. These lines basically are the grain boundaries. So basically what is happening over here, that this is the misalignment uh, of uh, crystallographic orientations while solidification. So these causes these boundaries. For example, if a metal is being solidified from this area, and the other uh, from the other part of the metal is solidified from this area, so they will meet on this boundary, causing a grain boundary. Okay, so the grain boundaries have high energy and are more chemically reactive. Since these are very highly reactive and chemically more active with the higher energy, so these are usually which are causing the area defects. So you can see there are two types of grain boundaries. One is a small angle boundary or a low angle boundary, and the other one is a higher angle grain boundary. So you can see that this is a grain in which the atoms are aligned in a direction, in this direction. Let me change the color again. In this direction, you will see that. But in the other grain, the atoms are aligned in this direction. So the angle produced uh, is a very high angle. Okay, so we call it a high angle grain boundary. But if the other grain, you can see as in this part, the other grain having these lattice arrangements, and the one which we have has these arrangements. So the angle is not that much higher, so we call it a small angle grain boundary. So in a higher angle grain boundary, the chemical reactivity would also be high than a small angle grain boundary. Then we have twin boundaries. So atoms on one side of the boundaries are located in the mirror image position of the atoms on the other side. So these are also kind of grain boundaries in which you can see that a twin plane is being formed. This is a twin plane in which you can see this is the mirror image of this plane. So both these planes are mirror images of each other. You can also see this in this part as well. and this part as well, and it would be continuing with this plane. Okay, the region of materials between these boundaries are apparently appropriately termed as a twin. This is termed as a twin. Annealing twins are typically found in metals that have an FCC crystal structure, while mechanical twins are observed in a BCC and HCP metals. So when we'll be annealing it out, we'll be annealing an FCC crystal structure, we'll be getting these twins, and in BCC and in HCP metals we can get these twin boundaries while uh, applying a stress, a mechanical stress. Okay. And then we have volumetric defects, in which in the volumetric defects we have pores, we have cracks, we have foreign inclusions. Again, these are called impurity atoms and other phases. The foreign inclusions are the atoms which we do not want in our alloy, or we don't want that in our chemistry. Okay, so you can see that here that these are the certain pores which can be caused by a gas particle, which can caused by a foreign inclusion. Then we have we have a crack. These cracks can be formed while solidification, since the amount of heat energy lost while solidification is not uh, with the same rate. So sometimes we get cracks. You know that metals while cooling they contract. So sometimes they tear it out from between. So this causes a crack, and these basically are the stress concentration points from which material will fail. So we have the spores, and you can see over here that in this micrograph we have a foreign inclusion, which is not which should not be here in the alloy, in the solid station of the alloy. So normally occurs during the processing and fabrication of the process. So we should try uh, not to get these, because these usually cause failure in long term, quick failures, and sometimes a catastrophic failure, which does not give an indication that the material will be failing. Even though the material is very ductile, still they are catastrophic due to certain cracks, pores, and foreign inclusions. So in order to observe these defects, these line defects, point defects, area defects, and volumetric defects, we use certain microscopic examinations, in which we have optical microscope, which we also have in our lab. Then we have SEM, scanning electron microscopy. Then we have TEM, transmission electron microscope, and we have SPM, scanning probing microscope. So we'll not be going into the detail. We'll be just discussing that scanning probe microscope has a resolution of 10 power minus 10 to 10 power minus 7 around. The transmission electron microscopy has a resolution of 10 exponent minus 10 to 10 exponent minus 4. So similar, the SEM electron microscope has a resolution of 10 exponent minus 9 to 10 exponent minus 3. Optical microscope has a useful resolution of 10 exponent minus 7 to 10 exponent minus 3 around. So, and we can, what resolution we can see from our eyes is 10 exponent minus 4 to 10 exponent minus 1. Okay, all these are in nanometers. So the amount of or the quantity which we have to view, so according to that we'll be choosing our microscopes, that how deep we want to go. One thing I like to identify over here, that there are two things. One is the resolution, and the other is the magnification. So the magnification is basically how how much you can magnify an image, okay, how much you can zoom it out, how much you can zoom in your image. And the resolution is defined as how you can separate two parts in an image very clearly. So the more clear you can separate two parts, the more the higher resolution it has. But in the magnification, you just zoom in the image. Okay, so the higher the resolution ranges of a microscope, the more accurate information it provides us. So that is all. Okay, thank you.